Hey everyone, this is Sina with another episode of Into the Bytecode. My guest today is Uma Roy, the co-founder and CEO of Succinct. So in this conversation, we talk about SP1, the zero-knowledge virtual machine they've built that allows proving the execution of arbitrary Rust programs. So we really dig into how SP1 works and try to get an intuition for how it's architected. We talk about how it uses Plonky 3, how it uses Starks, how it does recursion, and a bunch more things. And we also talk about some of the early things that people are building with SP1. For example, the recent project that allows any OP stack rollup to start using zk validity proofs and become a zk rollup. I thought Uma did a really good job explaining how this stuff works, and I hope you enjoy. So I thought as a first question, I'm curious how you actually ended up working on Succinct. And if you kind of think back to that period in time, were there particular moments that you remember kind of having the aha of like, this is what I want to go focus on?
Yeah, so I've always done a lot of math. And I remember actually the founder of Xerox Park, who I believe maybe you've had him on your
Yeah,
show.
Mr.
He's
Gubsheep.
Yeah, Mr. Gupsheep. He's a very good friend of mine, and he was telling me about ZK and how it's so, you can prove a statement and you don't even have to reveal all the inputs to that statement. And I thought that was very, very magical. And then I dug into the math and I was reading all this math stuff on the internet, and I thought it was super cool. And yeah, I think one day I was like, oh, ZK seems both really technically important, like it's technically super interesting and has all this math that I love. And then also ZK has this huge impact on crypto. Like it feels like the future of scaling all of blockchains needs ZK. And then the combination of those two things I think was very powerful and also what made me very into this space.
Mm. Well, I thought I would be interested to dive into SP1 and what you're building, at a deeper level of abstraction than maybe one would usually do. And maybe this is an opportunity to bring in some of the math without getting us lost in the sauce. But I think there's both people who might use SP1 as a library, but also folks who are just generally interested in ZK and have been interfacing with it more as a black box, but are interested to get more of an intuition of what's actually going on, what's the ground truth. So yeah, this is a big question, but can you help me understand how SP1 actually works? Like what is happening under the hood?
Um, yeah. I mean, I think at its core, it's pretty simple in some ways. Like implementing it is very difficult and complex, but actually what's going on is not so hard to understand. So, um, maybe it's helpful to talk about like what ZK used to be like and then what ZK is like with SP1. So previously, when you wanted to do ZK, well, what does ZK let you do? It lets you prove that some function, when run with a certain set of inputs, results in some output. And also optionally, you can hide the inputs to the function, which is really useful for like privacy. And so in general, like those types of statements you're trying to prove are like, oh, I have a bunch of transactions, and then when I run the EVM or like the Ethereum virtual machine, and I process all those transactions, in the end, the result is that Uma has, this many dollars and Sina has this many dollars. And these are the balances, and this is like kind of the state of the world. So that's like the type of functions you're trying to prove. Historically in ZK, and I'm sure you maybe know a little bit of this, to actually make your function ZK provable and generate a ZK proof of it, you have to write it as what is called a quote unquote circuit. So basically you have to write your function in this very specific form so that then we can like go generate ZK proofs of it. And in particular in the circuit world, you kind of, well, it's complicated to describe, but it's kind of similar to like writing this very low level like assembly kind of version of your function where you kind of break it down into like add gates and plus multiplication gates. So you have like, basically I take my function and then I just break it down into like the pieces that, and the only sub components I can use are like addition and multiplication. So that is really brutal, because usually you'll be trying to express like some very complex statement, and the only tools you have available are like plus and times. And so that was like kind of the old model of ZK. I mean, okay, that's not, when I put it that way, it sounds really, really bad. Now in practice, actually you can express any computation using plus and times, and like you can have like libraries and you can string everything together, but it is very difficult, and it was really bad. With SP1, what you can do is you can just like write normal code, like you just write normal Rust, and then you can generate proofs of it. And I guess when I put that contrast, it seems like, 100x improvement, and it is. Now what's actually going on underneath the hood is that you have Rust code. And so in SP1 world, you, as a user, you take your function you want to prove, you write it as normal Rust. It gets compiled to RISC-V. And RISC-V is this instruction set. That's a reduced instruction set. That's what the R stands for. And it, has like, definitely less than 100, probably less than 50 opcodes, which is like, okay, add, and multiply, load, store to memory, stuff like that. Like it's a very normal instruction set. And then SP1 proves the execution of the RISC-V ISA. And so what does that actually mean? It means like, okay, when I have a program running in RISC-V, and this is true for like any instruction set, you have this notion of like the program counter, or also known as the PC, which basically tells you which instruction in my program am I going to run. And then for every instruction, there's like a valid state transition for that particular instruction. So for example, if I'm doing an add instruction, I need to load 2 operands from registers, then I need to add them, and then I need to store that value in a destination register. And so in our world, basically, in SP1, we basically prove for every single instruction in the ISA that transition was done properly. So we prove that the program counter was incremented properly. We prove that all the register values that should have been updated were updated correctly, with the correct result after computing it, and stuff like that. And behind the scenes, the way we actually do that proof is we do break down basically proving every single RISC-V instruction into these circuits that are like just add and multiply and stuff like that. So behind the scenes, we are kind of still doing the old circuit-based stuff. But so it is very difficult and painful for us, but then for our users, it's really simple because they just write Rust, it just goes to RISC-V, and then we can just prove it. Yeah.
Yeah, that makes sense. And I feel like instruction sets and virtual machines might seem kind of mystifying from the outside, but they're actually very, very simple. It's like it's basically there's a list of instructions. You compile a program down into a set of instructions, which is basically what the binary or the bytecode is. And then you start stepping through them one at a time. And each of the instructions has a very simple meaning of, like you said, like take this 2 pieces of data, add them together, store it in a third slot of memory. And you're kind of proving that each of these instructions has executed correctly through the course of the program. And through, and then that whole proof, when it's given to someone else, shows that this program basically executed correctly without them having to step through the entire thing.
Yeah, exactly. Like we just prove that when you run your program with like the program counter starting in a particular spot, it always has like a canonical start location, and you run all the instructions in sequence. And so each instruction also tells you like what the next instruction should be. So when you run each instruction in the correct order, in the end, you get like some state of the world with like this particular memory, these particular outputs, stuff like that.
Yeah. And so let's dig into how these instructions are transformed into circuits and that. And the kind of underlying proof system that you're using is from the Plonky 3 toolkit. How does that work?
Yeah, so basically the particular protocol we're using is known as like the Fry protocol, and in general, like we're using the Stark's kind of line of work. So basically, how it works is, well, okay, Starks are basically a way of like proving these kind of statements using hash-based cryptography. So there's also snarks, which people might have heard of, and okay, I mean, this is getting Starks are a type of snark, but usually like what's happening. So popular snark protocols include like ROT16 and Plonkish KZG, and historically, basically, a lot of proving systems have used elliptic curve cryptography. Halo 2 also does this, or the Halo 2 fork that a lot of people in the Ethereum ecosystem use. Um, so yeah, there's kind of two major families that are commonly used, which is like elliptic curve based cryptography and then hash based cryptography. And then this we do all our stuff over with using hash based cryptography. And so we use like Starks and Fry. Underneath the hood, what basically happens is, so for each instruction, um, we have a main CPU circuit where basically what the circuit looks like is you have like a bunch of rows in a table. So each instruction is a single row. And basically, um, the state, you can think of like a row as like approximately like the current state of the world when you want to execute that instruction. And then the next row is like the next state of the world after executing that instruction. And for every single instruction, we have a bunch of constraints that say like, okay, the transition from like this current row to the next row needs to follow certain properties, and then we write like a circuit to constrain those properties. So for example, for addition, we like constrain that like, oh, the next row's like destination register value is equal to the addition of the previous row's like input register operand values, and we write some like circuit to basically constrain that addition opcode. So we'll say something like, okay, when the instruction is an addition opcode, then you apply these kind of constraints. And we do that for every single opcode. Now, this is like a really, really oversimplification of what's going on. Like, in reality, behind the scenes, we have our CPU, we call it a table. So we have like our CPU table or circuit. Now, if you had to put all of the information for all of the operands in that one table, your table would be super wide. Like, it would just have like a lot of information. And that's like very slow to prove. And what's interesting is like you're only ever dealing with one operand at a time. So if you have kind of all the logic in every single row to deal with every single possible operand, but you're only using a subset of it, then it's not like super efficient. So in practice, what we do is we actually have different tables for every opcode. So for example, we have a different table or circuit for addition, where basically we constrain that like that table is like actually pretty small. It's not that wide. It just constrains that like if I have two operands and I add them, it results in a third operand. And it just has all the logic and all the related information you need to actually do the constrain. And then we use this lookup argument called the log derivative lookup argument. It's also informally called the logup argument. But basically what that does is in our CPU circuit, we just look up that like our two operands plus and the third operand are actually like additions. So we look that up in our add table. And then the real benefit of this is that we get to save a lot of area. So in the CPU, our CPU can be like pretty thin because it's just doing these lookups to the particular table that is used for the particular operand at hand. And that I think that's much closer to the reality of what's going on. But yeah, and then underneath the hood, what's happening is like then you take all these tables. You do this like variant of Fry called like multi-table Fry, where you can basically generate one Fry proof for a bunch of these different circuits at once. And then at the end, you get one Stark proof for all these different tables that prove your statement.
That makes sense. And then you guys also do this sharding thing, right? For programs that are particularly large.
Yeah, exactly. So if you want to run a program that is like really, really long, there's kind of a limit to how long your table can be. So you couldn't have like a billion rows in your table, because in the protocol, what happens is there's like an FFT step that's like n log n. And so you'll like run out of memory. Like you'll run into like very practical limits very quickly, where it's like you'll just run out of memory on your CPU and stuff like that. So sometimes we'll want to prove statements that have like a billion rows, like there's a billion instructions being executed. That's actually pretty common. So for example, if you want to prove the execution of an Ethereum block, it can generally be a couple 100 million instructions to even like a couple billion instructions in some cases. And so, and we want to be able to prove programs of like arbitrary length. So what we do is we break up each program into shards. So we first execute the program. We'll get a billion instructions. We'll chunk them into shards of like 4 million instructions each, roughly. And then we'll generate proofs of, each shard's execution, which is pretty simple. It's just like, okay, the program counter at the beginning of this shard was this. We just run all the instructions. At the end, the program counter was this. And we'll do that for every single shard. And then we'll combine all the shard proofs together. So each shard gets its own proof. And then we will take 2 shard proofs, and we use this recursion system where basically we verify those 2 proofs in a Stark itself. And we verify that like, the program counter from your first thing, the last program counter from your first shard is equal to the start program counter of your second shard. And so then if those 2 proofs are both true, then you know that you have a proof that basically works with the first program counter of the first shard and the last program counter of the next shard. So it's like covers the whole range. And then you get 1 proof. So basically you take 2 Stark proofs and then you verify them both in a Stark, and then at the end you get 1 Stark proof. And we do this for many proofs. So for example, sometimes in certain programs we'll have like 100 shards or 1,000 shards. You can kind of do this like in a tree-like structure. So you just do 2, 2, 2 at a time. You get the next layer of your tree. You do it again. And then at the end, you just end up with 1 Stark proof. That's the full execution of the entire program.
So cool. It's wild that this stuff is real.
Yeah, it was a lot of pain to implement. It's very difficult.
Yeah.
But and then for the recursion thing, what's interesting is, so normally you could think, okay, well, how would you implement the recursion thing? Maybe the most naive way is you just write a Rust program, and you write a Rust program to verify 2 Starks, and then at the end you just run that program to verify 2 Starks, and then you get a new proof. Like you're basically using SP1 on itself recursively, kind of. Now that actually does not work, because when you try to do that, there's way too much overhead. Like the RISC-V instruction set, it's going to be way too many cycles to actually do that. So in practice, what we do is we made a new VM. So we made like our own instruction set that's specialized for recursion. So that's specialized for verifying Stark proofs. And then we actually have a recursion VM where basically we have another VM that verifies 2 of these like Stark proofs. And we wrote a program in our own VM, so then we had to build like a baby compiler to basically like write a Stark verifier in our own DSL, compile it, and I'm using like air quotes, like compile it to our own recursion ISA, and then we had to write a bunch of constraints and logic to constrain our own recursion VM. So not only did we build a RISC-V VM and all the circuits for that, we also had to come up with our own recursion ISA, build a DSL to write programs in it, build a compiler to compile to the recursion ISA, and then write a whole bunch of circuits to constrain the recursion VM and recursion ISA to then do recursion. So yeah, that's actually very, very difficult as well. But yeah, that's the whole system.
That's wild. So you're also using Plonky 3 though. So where is the kind of interface between what you don't do and you're pulling in from an external library?
Yeah, so Plonky 3 is this really great library built by the Polygon team, in particular, Daniel Lubrov and the Polygon Zero team at Polygon. And basically, it's an implementation of Fry, in particular the multi-table Fry. So we use Plonky 3 as our implementation of multi-table Fry. So we did all like the constraining, we did all the recursion stuff, and then when we actually want to run the Fry protocol, we call like Plonky 3's methods for that. Yeah.
And so one thing about this general field is that it's evolving very quickly, right? The performance characteristics are continuously improving. So what's involved with you kind of upgrading your proof system over time if you want to do that?
Yeah, so the field in zk does move really quickly, which if you're building a system, it is like it's hard to balance like taking your existing system and squeezing all the performance you can out of it versus like trying to make a bold bet on like, okay, we're going to change like and upgrade to the latest stuff. I will say within the field, I feel like there has been kind of a consolidation around small field hash-based schemes. So historically, there's been a lot of teams working on this like elliptic curve-based schemes. And the kind of challenging part with elliptic curve stuff is you generally need to work over a very large field. So like basically your circuit is over this like 252 or 254 bit field, which is pretty large. And the reason a large field is bad is like in your normal CPU, like your laptop or whatever, generally arithmetic happens over 32 bits or 64 bits. And when you're trying to run operations over a very large field that's like 252 bits, it's very slow to do on like a normal CPU or even a GPU. So there has been a trend for a while where people are just making the field smaller and smaller, and that results in like really great performance. So for example, like going from 252 bits to like 31 bits, you just divide those numbers, it's kind of like an 8x. And it's not exactly correct, but like basically you can think of like, oh, I made my field 8x smaller. Okay, my proving performance goes up by 8x. And so our proof system is over the baby bear field, which is a 31-bit field. And then, okay, one thing is, so you can't do elliptic curve stuff over a 31-bit field. Now, thankfully, the Starkware people, and there's been this line of work with hash-based schemes. And you can do hash-based cryptography over the small field. And so that's kind of like the technique that us and a lot of other people in the industry are converging on. So for example, zkSync, Polygon zkVM, RISC0, Valida, a lot of people have been using these like smaller hash-based fields. Plonky 2 library, all those things use like small field with hash-based cryptography. So, I guess I didn't answer your question.
So the general architecture will remain the same there's this tension of squeezing as much as you can with what you're building around the proof system. But even if you want to upgrade it, it seems like the field is generally converging on one architecture, which maybe makes it easier to kind of swap this out in the future.
Yeah, I think another thing is, for example, we use Plonky 3, which is an open source library, and there's also a bunch of consolidation around that. And SP1 itself is also very open source. Like, this proof system's fully open source. I think we've tried to make it like a pretty nice developer experience. We've actually had a bunch of external teams fork it. So, for example, the Lurk team, they have a new name now. I think it's called Argument. They forked it. They added their own precompiles, which maybe we'll talk about in a little bit. And they've kind of contributed back to SP1. And so you kind of get these like open source shelling points around Plonky 3 and like SP1. And that also, I think, helps with upgrading it. So for example, there's this new hash-based proof system called CircleStark that uses a different field than the current one we use. And Plonky 3 is implementing it, and then when Plonky 3 implements it, you could imagine that like we just are able to pull it into SP1 and upgrade to it. And so, that's, I think, something I find really magical about crypto is like everything's open source, and that you can have these like really positive open source collaborations that you don't really see happening in Web2 or other industries. And so I'm also hopeful that that's something that can help us kind of like, be at the bleeding edge of all this stuff and collaborate across ecosystems to have all of us be at the bleeding edge.
Right. Like if a lot of teams are using SP1 in their applications, then a new proof system to kind of get distribution would go and do the work themselves for getting integrated into SP1.
Yeah, exactly.
Yeah. I was talking with my friend Zach Obrant earlier, who I think worked with you on a project.
Oh, yeah.
And he was, before we get into the ZK rollup stuff, which I do want to talk about, one of the things he said was that it's been really impressive to see how you've kind of improved the performance by orders of magnitude. And how have you been able to do that? And maybe this ties into some of the precompile stuff. But again, what's an intuition around where you're looking for those improvements, how you're kind of like iterating on the system?
Yeah, so one of SP1's biggest innovations was the system of precompiles. And so what a precompile is you can kind of think of it philosophically as a way to have like ZK assembly. And again, that's in air quotes. Like you have a very specialized circuit for a certain very expensive operation. So for example, the catch-ack hash function or the SHA hash function or verifying, an ECDSA signature. You have a specialized circuit for doing that operation. And so instead of paying a bunch of instructions in your CPU, so for example, for for verifying an ECDSA signature, if I were to just write it in normal Rust, I think it will take 1 million cycles. And with our system, basically what you do is you have this specialized circuit for verifying an ECDSA signature that does kind of like a lot of the heavy lifting. And it like inlines a lot of like memory access. It does a lot of stuff that like is really specialized. And then what happens is basically you take those 1 million cycles and you turn it into 40,000 cycles. So that's like a 20x. And intuitively, like you can think of it very similar to assembly. That's kind of why I made that analogy, where it's like normally, even when you and I write normal programs, we just write in normal code. And then underneath the hood, actually, oftentimes, even for cryptographic libraries, like if you look at Rust Crypto or any implementation of like any cryptographic library, they'll have a lot of like pretty ugly assembly code that's like specialized to your CPU architecture, that's like making use of vector instructions that is like for that particular computation, since it's so like sensitive and it gets called a lot of times, you like really hand write it to squeeze every last bit of performance out. And so you can think of our precompile system as doing basically exactly that. Where we hand wrote a circuit very specialized to these operations, and got it working. Now, that's our precompiles, and in practice, like our order, the reason why SP1 is so fast, often by an order of magnitude, is that these precompiles are super, super effective. So, for example, a program that normally would take 2 billion cycles in SP1, when you use precompiles, it'll take like 300 million. So that's like a, almost 10x right there. And generally when you have 10x less cycles, it's also 10x less proving time. And I think one of our key insights, and I often think actually some of the best insights sound so obvious or like in retrospect, but when we came up with this idea, it wasn't even clear to us that having these precompiles would be like super worth it. Like we were kind of just like, well, let's implement the precompiles. For most of the use cases we're interested in, like bridging and rollups, most of our CPU cycles are spent in these like hash functions and signature verification. And then the rest of your business logic, that's like, oh, like is the gap, like is your nonce equal to like your previous nonce plus one and stuff like that. We're like, oh, I mean, that's like relatively less expensive in terms of instructions. So we implemented these precompiles. And then I remember there was like a day where we were testing our precompiles, and there was this one program where we literally saw the cycle count go from 800 million to like 30 million. And we're like, oh, wow, like this is super effective. But I think that was when we decided to build our architecture in that way, it was not super obvious to us exactly how effective it would be. Like we thought it might be like a 2 to 3x, and then in many cases it was like a 10 to 20x. And so I think, yeah, that even exceeded our own wildest expectations. And in hindsight, you're kind of like, oh, this is like super obvious. Like even on a normal CPU, when you run Ethereum blocks, actually a lot of normal CPU time is spent doing the catch-check hash function. So you're kind of like, oh, that also would make sense in a ZK context that you'd want to write this like ZK specific assembly and like hook it up to the main, your main RISC-V part. But yeah, I don't think that was very apparent to many people because no one had really built a system like that before. And also getting it working from a cryptography perspective is pretty difficult. Like there were certain like novel algorithms and techniques like we had to come up with. Like we have this like global shared randomness system that basically no one else has. That's pretty innovative, and we came
What's
up
that?
with. Basically, to make the precompiles actually work, we have this like 2-phase prover. Where in phase 1, we like go through the whole computation, generate it, and then hash all of it to get like a shared global challenge that then we can use across our entire computation in phase 2. And that's just needed for our but yeah, that's needed to like make everything cryptographically work. But yeah, like we have this like 2-phase prover system to make all this precompile stuff work. Like it's not so easy to really get working in an efficient way, and a lot of our challenges and a lot of time, engineering time we spent was to get this precompile stuff to work. It's not very easy to do it. But yeah, I think now like you'll see like a lot of people talk about precompiles, and a lot of people are adding precompiles to their systems, and it's kind of like, I think at this point it's kind of become like super obvious that this is the way the zkVM performance is going to kind of match the performance of, circuit-based systems and actually be practical. And so a lot of people are doing it now, but I think even at the time, like even when we started, it was not even obvious to us. And I think it's been like super magical to see it like play out and work super well. Yeah.
Into the Bytecode is sponsored by Splits. Are you tired of sacrificing security for usability? Splits believes it's still way too hard for teams to self-custody their on-chain assets. They're building a new kind of internet-native bank on top of Ethereum. Splits makes it easy for teams to manage the whole lifecycle of their finances, from structuring revenue-sharing agreements, using payment flows like splits and waterfalls, to managing those earnings once you receive them, using passkeys and smart accounts. Splits is being used by teams like Protocol Guild, Zora, Songcamp, and others. I'm a big believer in them and recommend checking them out. You can learn more at splits.org. Yeah, that makes sense. And you're kind of like tuning the VM to the type of use cases that you expect to happen, right? And if you kind of like benchmark the performance of these programs and certain functions are just getting hit over and over again, it makes sense to optimize them. How do you think about like security and like the testing of these systems? Because just hearing you describe it, it feels like, this like crazy deep like math, and you're implementing these things, and ultimately this machinery will be used to prove the execution of a, say, ZK rollup, right? So you want to know that it's happening correctly. How are you thinking about Yeah, how to kind of like build into that security over time. Like how do you what are your mental models around that?
Yeah, security is always like a super, important area, and like, hard to. It's always like very hard and requires a lot of effort. I think there's a couple of things. I think first of all, by being fully open source and also using other open source libraries, we get a lot of that like compounding effect. Like so, for example, we use Plonky 3. The Polygon team got that audited. There's other people using it, and hopefully, like the security story around that compounds. I also think security is like a process. I think being like, oh, our thing is 100% secure at this point in time is kind of meaningless. Because first of all, the systems are changing. Like we're optimizing stuff. We're coming up with new algorithms and deploying them. And then also like security itself is like a living process. Like you have many people look at the code base, and you have more people look at the code base. And we recently hired like this amazing auditor to join us full time, and like he's just going to look at the code base for his full-time job, and he's always going to be looking at it, right? So yeah, I think security is definitely like a process more than just like, oh, we got an audit report and now like, okay, it's secure or it's not
Yeah,
secure.
you never know for sure.
Yeah. And I think also, but as for example, with SP1, we had like a public competition, at least for our core RISC-V where, we had people across the world. I mean, it was like an open forum, and they participated in the competition, and, found, bugs and stuff in SP1's RISC-V. And so you can imagine that, like, as the system gets used more, and then there's more and more people also using it and forking it. That's why I actually view a lot of our forks, like, very positively, because it's like, okay, that's just, like, more eyes on the code, that can like kind of find new problems, and as you have like more diverse teams, more diverse people looking at it and using it in production, you can get better and you can feel better and better about the security. Like for example, I feel like that's even true with Ethereum, right? Like Lido, for example, has been used for a very long time, been used by a lot of people, and now people feel like better and better about its like security properties. And I view it as like very much similar. It's just like these things will get used to get more and more used and more looked at, and we'll fix stuff as it comes up, and in 5 years I feel like hopefully we'll feel very, very good about the system.
Yeah, it's like the passage of time with value being at stake, and something just gradually becomes more and more Lindy as time goes on.
Yeah, 100%.
Yeah. Okay, so maybe digging into this rollup stuff now, because this was so cool for me to learn about, and I saw your presentation about it at Greenfield and Frontiers. But basically, you apparently, without much complexity, using SP1 and Reth and Kona and a couple of Rust libraries that can basically execute Ethereum blocks, you built a way to turn any OP stack optimistic rollup into a ZK rollup. Can you explain how that works?
Yeah, so to kind of cover like the OP stack, basically Optimism, they run a layer 2 Optimism mainnet, but then they also have this OP stack, which is this like open source technology for anyone to kind of deploy their own rollup. And from day one, I think the Optimism team actually deserves a lot of credit for building the OP stack in a super modular way, where they first of all built it fully open source, and they also built it where, like, for example, you can swap in and out certain smart contracts, or you can really modify like the rollup system, and the code's really well documented to make it easy for other teams to do this. And so that's actually like what we did. We took the OP stack and we swapped out one smart contract. So instead of having their fault proof system, basically they have one smart contract where like the transactions get posted in blobs on chain, and then you have one smart contract that has like the state root of the rollup against which like withdrawals and bridging is done. And normally that smart contract is the correctness of that smart contract is ensured by their fault proof game. So that's like their optimistic fault proof, interactive, challenge, bisection, blah, 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 whatever. What we did was we just replaced that smart contract with a zk version of that smart contract, and the diff is actually pretty small. It's like 50 lines of code, where whenever you post a state root, now you just alongside it post a proof, and you verify that proof, and then you know that state root is correct. So we replace that smart contract with the zk version that verifies proofs, and then we took the kind of like off-chain agent that's running, that's updating that smart contract, and we modified it a little bit so that it actually like generates the proofs using SP1 and using our kind of like proof API, and then keeps that smart contract updated. So it's pretty awesome because basically in the end you can take any OP stack rollup and you can do like you can deploy one smart contract on chain. You can spin up one very lightweight service because the service itself is not generating proofs. It's like dispatching out to our API to generate proofs. And it keeps that smart contract updated. And then boom, you have fully converted your rollup into a full zk rollup. So, and then, yeah, I think the beauty of using SP1 is that like there's a lot of benefits. So historically, if you wanted a full zk rollup, for example, like the zk rollups that exist today, like zkSync or Polygon zkVM or Scroll, normally you'd have to have this like very sophisticated advanced team of like 30 cryptography PhDs coding a specialized circuit of the EVM for your zk rollup. So you literally have this like really long, complicated code base that's like hundreds of thousands of lines of code to code like the actual state transition function logic of your rollup. And I mean, those teams did that. Like, it's possible. It's very difficult. It takes a really long time. It's very hard to maintain. Like, when Ethereum upgrades, you have to, like, change all your circuits. And overall, I think it's not a fun time. Also, a lot of those rollups aren't even type 1. So, for example, they have, like, differences with the EVM, in particular, often for, like, how they compute the state root and stuff. So, yeah, that all, like, is very difficult and complicated. And so with SP1, what's really nice is you just take Reth, you take Kona, which is like Optimism. Optimism has like a Rust library that they open source that implements their state transition function in Rust. So we take like Rust, we take Reth, we take Kona, and we just take all those programs and we run it in SP1 to generate a proof of the state transition function. So it was literally like Zach and one engineer on our team. They got it done in like a month and a half. Where they just took a Kona, put it in SP1. It was like 500 lines of code. And then boom, you can get a zk proof of Optimism state transition function that you can use to turn any Optimism OP stack rollup into a zk rollup. And by the way, it's like fully type 1. So it's like fully EVM compatible. It uses the same code. When things update and change, like we just do cargo, update, Kona. Like it's all very simple and nice. It's really maintainable. It's really testable. If you want to customize your rollup, you want to add new precompiles, you want to like do some magical, I don't know, like make the balances like yield farmable or whatever it is, you can also do that. So it's kind of like the best of all worlds. Like you get the amazing DevX, the customizability, the maintainability, but then you also get all the benefits of zk, which is like the withdrawal window is not 7 days. It goes down to like 1 to 2 hours. Interoperability is a lot nicer. Yeah.
Crazy. Yeah, it's like the fact that these pieces of software are just composable in this way, and you can drop in 2 libraries into SP1 and it works is so cool. Are there any? It seems like you're saying this is just like a strictly better approach. Is there a steelman to the other side that it still makes sense to kind of write custom circuits for these things, or do you think that no longer makes sense?
Yeah, I think the custom circuit people might say like, oh, the zkVM is still a bit expensive. To put some numbers behind that, so today, if you do the things I described, I think the proving cost per transaction ends up being, well, it really depends on your rollup and stuff like that, but it ends up being less than 1 cent of proving cost per transaction. So I think it's between like 0.5 cents to 1 cent. And SP1 has a lot of improvements in store. There's also a lot of like optimizations we can do in the Kona program and also like Optimism's protocol itself. Like, there's some small design decisions Optimism made. It's not really their fault that, like, you know, they weren't thinking about this use case, but, like, there's very small tweaks to their protocol that could make all this stuff, I think, like, 2 to 5x more efficient. And I think all those things will stack to make that go down by 10x. Like, I think we will, in the next, like, 6 months, have 0.1 cent proving cost per transaction, fully zk rollup. And, like, I don't know, 0.1 cent, I don't know, that's as cheap as Solana. Like, that's very cheap. I think that seems, like, quite reasonable. So I think I would say, like, hey, it's already, like, very cheap. It's so much more maintainable, all this stuff. And I really think the era of doing custom circuits for this stuff is over. And I think, like, one important thing to kind of understand is, like, the intuition behind why. Like, I actually never thought it would be possible for a zkVM to outperform custom circuits. Like, that does seem really crazy. And I think So I do want to provide some intuition for, like, why I think that's the case. So I think from a theoretical lens, of course, if you handwrite a custom circuit for exactly your computation, it can have better performance than SP1. Like, that is, of course, that's almost, like, definitionally true. But I think from a very practical perspective, because SP1 is such a broad platform, we can always spend the engineering time to squeeze, like, every last bit of performance out of it. So, for example, we wrote an SP1 GPU prover. We like, really optimized our cloud deployment of SP1 to basically make it, like, pipelined, and you run into, like, really weird bottlenecks. Like, even, like, for example, downloading files sometimes becomes your bottleneck and stuff like that. And basically, like, we've really optimized every single corner of SP1 to be as fast as possible. And are continuing to do that. Now, in a circuit system, it's really difficult to do that because you have your circuit for your one use case. And then it's like, well, am I really going to spend 10 engineers to write a GPU prover for this if it's just only benefiting me and my one company and my one use case? And then, oh, by the way, like, our circuit might need to be redone when a new proof system comes out. For us, it's, like, a really different calculation. It's like, okay, when we make SP1 10% better, literally every single one of our customers benefits. Like, any roll-up team using SP1 benefits, any bridge team using SP1 benefits. I think there's, like, dozens of people experimenting and building with SP1 at this point. So it's like all those people simultaneously benefit. So for us, it was worth the engineering resources, which were quite significant, to build a GPU version of SP1's prover. It was like a no-brainer. Like, oh, we have to do this. Whereas, no, I think the ROI there just does not make sense for, like, a custom application-specific circuit. And so that's why I think, just in terms of practical reality, it's very difficult for custom circuits to kind of live up to a general-purpose zkVM. Because, like, the platform is so general that in the end, it can be a lot more optimized. And I think that's only going to become, like, more and more true, right? Because it's like, more people are going to use SP1, we're going to, like, hire more people and really optimize it more. And then it's just this, like, flywheel that compounds more and more over time. And I think already, actually, running, like, Reth plus SP1 is faster and cheaper than, like, certain current, like, ZK circuits specialized for the EVM. And I think that's only going to, like, become more and more true, basically. So, yeah, I don't see that trend, like, stopping anytime soon.
Mm-hmm. Yeah, those set of arguments definitely make sense to me. How are you thinking about where SP1 gets used? How big of a focus within that are rollups, and, like, what you're pushing on here, and, like, what are the other areas, like, let's say in the next 1 or 2 years, that you think there's, like, a real promise of ZK making a difference?
I think rollups needed ZK, like, 4 years ago, honestly. Like, I think that's, like, a really burning, urgent need for rollups, where it's like, if you think about it, it kind of makes sense. Like, decentralization has an inherent overhead because everyone has to repeat the same computation. This is why, like, Ethereum is a world computer, but I like to say it's, like, a very bad world computer because it's very slow and expensive. And then ZK, like, obviously naturally solves that, right? Like, the verifiability of ZK is, like, the perfect complement to, like, the overhead of decentralization. So it just, like, makes sense. Now, I think zk is really the only way like Ethereum's going to actually scale in a sustainable way. You can do a lot of hacks, which is I feel like our current system of scaling Ethereum is like a bunch of hacks layered together. It's like, oh, we do this optimistic thing, but oh, your money's locked up for 7 days, or like, oh yeah, the optimistic teams are trying to do like this interoperability thing, but like, oh, like it only supports like 5 chains, and it's very permissioned, and it's like it's kind of a mess. So I think zk is like the only way like we're actually going to scale blockchains. It's just like time to become serious and actually scale blockchains. And I think zk is the only way to do that.
How do you think about interoperability? I think Ratan said that you have some spicy takes there about zk is the only way that interoperability is going to work.
Oh, yeah. I think that's like kind of what I was saying, where it's like, if you look at the optimistic rollup ecosystems today, like,
Yeah.
okay, there's this like infrastructure soup. Like, okay, because there's a 7-day withdrawal window, and that's like totally unacceptable to most people.
You don't get finalized.
Yeah, and your money's locked up. So then you have these like liquidity layers that are like fast bridging in and out. But like they don't like if you're trying to fast bridge out $100 million, they're not going to be able to do that for you. So then okay, like for that already doesn't even work for like people who have a lot of money on chain, or you can imagine institutions like needing that kind of capital available immediately. And then okay, but say that kind of works. I would argue that's still pretty bad, because now if I want to build my own roll up and deploy it, now I have to go lobby to like all these other like all these bridging companies and liquidity companies, hey, deploy on my roll up. And usually they'll be like, well, supporting a new roll up is like very complicated and difficult. Like, how much liquidity and TVL are you going to have? And then you're like, well, I'm just starting my chain. Like, and then it's, there's this chicken and egg problem. And so I think today deploying a roll up like kind of really sucks, because there's all these other actors and like set of infrastructure soup that's needed to make this stuff work. And I think fundamentally that's just because like the optimistic stuff, it's kind of like a clever way to securely bridge back to Ethereum, but it's not actually scaling much of anything. Like, all these actors that are running infrastructure still have to run a full node for the optimistic rollup. Like, they're not actually scaling. You're still repeating the computation. And so with zk, you don't have that. Like, you just verify zk proof. You eliminate the need for most of these actors. And it just works. Like, it's actually just scaling. Like, you can just verify the zk proof, and you verify the computation. You know what the new state root is, and that's kind of like the end of it.
So each of these L2s, each of these rollups will have kind of state roots for all of the other rollups, and those state roots will be computed as zk proofs.
Yeah. Like, I think the end game for all of this is like the Ethereum people implement single slot finality. Okay, this is very end game because this might take a while. There'll be like real-time zk proving for all the rollups, and then it's just like you have your verifiable database settling into Ethereum with a real-time zk proof that anyone else in the world, including other rollups, can just verify, and you just like have like it really does feel like one chain where you just like can instantly move money across like any ecosystem that you want. Like, I think that the only way we're gonna get there is with zk. That's done in like a scalable, sustainable way.
What do you think the asymptote of that is? Because for generating, collecting all the transactions and generating the proofs, like some period of time still needs to pass, right? Like, you're not doing that instantaneously. Or what does that trend to over time?
I mean, I think we will definitely get to real-time proving. I mean, obviously, I'm not saying we're like super close there today, but even with our systems, one interesting thing is, as I mentioned earlier in the podcast, we have this like sharding argument where like we take a really long computation and we shard it. And actually one nice aspect of that is you can start generating proofs for all those shards in parallel. So you basically distribute your proof generation computation, and you're using the same amount of resources. So from a cost perspective, it's actually slightly more expensive because there's like a overhead to distributing the computation. But from a latency perspective, your latency goes down a lot. And so we already have situations where maybe the total amount of end-to-end time is like 30 minutes to generate a proof for one block. But if we fully distributed it, you could imagine that we get the proof in like a couple minutes. And you could imagine that like that goes down even further, and you start getting proofs within like 30 seconds, or even like at some point, I think like 12, 15 seconds. So I think with a lot of these things, there are solutions to really lowering the latency that will come about as the proof systems get better and faster. And then also, for example, for us, like once we understand, like, hey, like the costs are cheap enough, now we're just going to laser focus on latency. There's a lot of stuff we can do as well to make it better on an algorithm side. So I think that will happen. I'm not saying it'll happen in the next 6 months. Like I'm very confident as P1 we'll get like 5 to 10x cheaper in the next 6 months. Like that is like a huge given. I'm not claiming we're going to have real-time proving in the next 6 months, but I don't think it's like 10 years out.
Yeah, that makes sense. So you were saying there's rollups, there's bridging. These are like 2 areas that you're really focused on. Is there anything else that you think like that you internally are really trying to push on right now?
Yeah, I think there's like 2 categories of zk broadly that I'm really interested in. One is like what I like to call upgrade the stack, where it's like we've built crypto, it's been kind of crazy, there's a lot of technical debt almost. Like I kind of view optimistic rollups as like technical debt, and it's like, okay, finally zk is really easy to use, it's actually fast, it's actually cheap. Okay, now let's go actually use it. So it's like, let's make every rollup a zk rollup, let's make every bridge a zk bridge, let's remove like all the multi-sigs and bad stuff that's happening that shouldn't be happening, and like let's like actually fix all these things that should use zk and actually make them verifiable and kind of like live up to the promise of crypto. So I think that's like upgrading the stack, like taking existing things, adding zk to them, make it work the way it should have originally worked, but we didn't have the tools back then. And then so I would put rollups and bridges into that category, where it's like every rollup should be a zk rollup, every bridge should be a zk bridge, and like, you know, there's a bunch of other on-chain applications, like everything that can use zk should use zk. And now it's like almost a weekend project. I like to joke to integrate a lot of this stuff.
What are the other big categories of this upgrade the stack?
It's a good question. I think rollups and bridges are the biggest ones. But like there's many different types of rollups, right? There's like different VMs of rollups.
Right.
You know, there's different constructions of rollups. Then there's, for example, things like Aglair, which is like, Aglair is not a rollup. It's not, this is Polygon's new interoperability protocol. It's not really a bridge. It's like an interoperability protocol. So things like that like don't neatly fit into like one or the other. I kind of like to, or there's these like multi-settlement rollup things. It's like, is that a rollup? Is that a coprocessor? Oh yeah, coprocessor is another big one. Where it's like off-chain compute. It's not quite a roll-up, but like it's kind of similar to scaling. So I think a lot of those applications should use zk, and often already do. And then I think the other one I'm really interested in is like real-world zk, where it's like, oh, how can we use zk in like a blockchain adjacent context? So for example, I think there's been a lot of recent excitement around like web proofs or like zk TLS, where basically you can like take arbitrary data that's like provided by, you know, various like internet companies, and then attest to it, and then selectively reveal information about it using zk. Or you can also, you know, or for example, there's a lot of like self-sovereign identity and like credentials and attestations that I think are interesting. Like for example, you can prove that like a bunch of other people or that you have like all these different credentials, and then really reveal some like sort of complex statement about it. Like for example, oh, my age is like over 18, but I'm not going to tell you my actual age and stuff like that. I also think like the notion of having like a verifiable database is also super important. For example, like you have these credit scoring agencies where, I mean, they could just like say your credit
They just update your score.
Yeah, they just update. There's no there's regulatory accountability, but I mean, these people get like hacked all the time and stuff. So it's kind of like that. I think that's an area that would really benefit from verifiability, where it's like, okay, when they update your score, you know, they have to show that like it's following some reasonable function, and it's you know, doing some reasonable thing, and not just like giving you random information. So yeah, those are all the kind of use cases that outside of crypto or like blockchain adjacent or just normal verifiability that I'm pretty excited about to see flourish. And some of those ideas, like I don't know if it's going to happen even in like the next 3 months. Like I think the roll-up stuff could happen in like the next N months, where N's pretty small. But I think it's like really important for people to be working on this like longer term stuff and see like how ZK can help in kind of like the real world beyond like our crypto ecosystem.
Totally. And this kind of blends into the other primitives like MPC and FHE, and like those are on their own curves of improvement and unlock whole other sets of applications.
Yeah, for sure.
Yeah. Very cool. Maybe as a last question, I'm curious, when you look at the life cycle of a, let's say in the rollup case, I decide to zkify my state transition function. In the life cycle of the proof being generated and verified, what are all the players that are like, what are all the different, if you were to walk through that, what are other players that are involved there? Just to like be able to visualize this life cycle from beginning to end.
Yeah. So generally you have some sort of end user application that wants a ZK proof. So that could be a roll-up team or bridge team. It could be like if they're decentralizing their sequencer, it could be like whoever is like responsible for posting it. Like, so you have like some user or proof requester that's requesting a proof. Then our dream is like they make one API call with their proof request information. So they pass in their program, they pass in their inputs, and then they basically will get a proof in the shortest amount of time possible for the minimal cost possible. And today, right now, we have an API where we basically do that. Like we have our own prover. We have an API and then we provide them the proofs. But we're also working on basically a decentralized prover network where one day it's not just us being able to provide those proofs and generate them. It'll be this protocol where like anyone in the world can just like plug in their GPU or computer and start providing capacity to the network and provide proofs and, like serve as this like kind of actor in the ecosystem. So, I think there's going to be like a prover network or some like just decentralized.
Why do that? Why have a prover network rather than you just do everything?
No, so it is a good question. I think, well, first of all, like actually generating proofs for low cost is like a pretty different, I think, skill than, for example, building the VM and doing all the algorithms and stuff ourselves. So as a very concrete example, oftentimes like you have to get a data center with a bunch of very low cost energy and, set up the prover nodes and manage them and stuff like that. And like, I don't particularly want our company to like, get into that kind of like business of like, setting up data centers and maintaining them and stuff like that. And you even see this in AI where like OpenAI and Anthropic and stuff, they like rent data centers from other people instead of like them doing all of it in-house. So I think there's like some notion of like, okay, well, first of all, I think it'll be better if we have this like open protocol where like people can compete and provide capacity to the network, and it's not just like bottlenecked on us, like having our act together. The other thing I think is really interesting is you can have this sort of like competition dynamic or aspect. So for example, with Bitcoin, they have this protocol for like mining, and then that really induced this like global competition for like who can have like the best mining ASIC. And you have the, these firms all compete. And you got like tremendous gains going from like CPU mining to GPU mining to FPGA mining to ASIC mining. You can imagine a similar system for like SP1 where you have this like global competition of like, all these people in the world where like they know if they can just like make it more efficient and really optimize everything, then like, they will get money for it. And then finally, I feel like the thesis of crypto is that you have these like open protocols and systems where anyone can participate. And then because anyone can participate and it's open, there's like less rent seeking from like the one person doing it. And instead you get like better outcomes for everyone. So it's like users get cheaper costs, and then those other people, they can like put in capital and time and effort, and then, they'll also get rewarded. So instead of us just like, being the only people who can generate proofs and like having this walled garden, instead, okay, let's make it this open ecosystem.
And you turn it into a market.
Yeah,
From a
exactly.
single player service, it turns into a market where there's competition and supply and demand and all those sorts
Yeah,
of
exactly.
things.
And like price transparency and like all these nice things. And so it's like,
Yeah,
well, if we're gonna be building in crypto, a lot of our customers are in crypto. Like, I feel like that's just like the right way
totally.
architecture to architect it. So, yeah, I think like having a network of these provers that can participate in like the marketplace. I think is like basically better for everyone, from like an end outcome perspective. And so that's why we want to build it in that way. Um, and then it is very much like the thesis of crypto as well. I feel like.
Hmm.
And
So
then
the developer calls this API right now. You're generating the proofs. In the future, there will be this network, um, and so there's these basically like node operators, which right now is just you, and
yeah,
you're running some hardware basically.
yeah, yeah. Right now it's like a network of size one. We're the only operator, and like we fulfill all the proofs. But yeah, like one of our big focuses is to like make that so that anyone in the world can participate. And then also you get like decentralization and like liveness properties too, which is, I think important for like a lot of our customers, and actually they care a lot about that. Um, and then yeah, after the network generates their proof, you get it, and then you verify it on some settlement layer. So like it could be Ethereum. If you're doing L3s, it could be like Base. It could be Bitcoin. It could be Solana. Like you verify. It could be your user's phone. I don't know. Like you verify the proof somewhere where it's useful. And then yeah, that's kind of like the pipeline.
Hmm. Do you see any promise for developing the software and the hardware together, or like hardware custom to the software, as has happened in other kind of industries?
Yeah, so this is basically like should we build our zkVM in a way that's like super hardware friendly? I would argue we actually already kind of do that, right? Like for example, the small field that we use is
Mm.
very hardware
The
friendly. So
reasoning for that is because of the hardware.
exactly. So we've already kind of co-designed SP1 for the hardware that we use, which is CPUs and GPUs. There's this kind of question of like FPGA ASIC um, design. I do think in the fullness of time that will come about, um, and but in many ways, I mean, in many ways, like there's a lot of advantages to being, for example, in a more general purpose hardware in the short term. For example, like the algorithms are changing pretty frequently, and we're coming up with algorithmic ideas. And I mean, I don't know if you've ever tried to like write FPGA code or certainly develop hardware. Like it's
Back in
very
school.
difficult.
Yeah.
Yeah, it like sucks. It's really difficult. And so it's kind of like for now, it's nice to like prototype and do the algorithms on a general purpose flexible hardware and be able to iterate quickly. And then I think at some point a lot of this stuff will kind of like consolidate and converge, and then I think it makes sense to do like FPGA ASIC for it. Um, I think there's like a question of like what time horizon is that relevant on? Is it like things will still be like kind of evolving super quickly for the next 2 years, or will it be 5 years, or will it be like 6 months? Um, I'm not super sure. There's also this question of like data movements. Like, for example, a lot of the process, like a lot of our prover right now is not even necessarily like compute bound. Like, basically, the hard part is like getting the data onto the device and then being able to turn compute on it. So, um, if you have like an ASIC for example, okay, for Bitcoin mining, it's like perfectly compute bound, right? Like you're just hashing something
Right.
like
There's
as many
like
times
no
as
state
possible.
basically.
Yeah,
Yeah.
there's no state. You put your initial seed onto the device and then boom, you just do as much like gates as possible. So for mining, an ASIC makes perfect sense. Proving is much more complex. Like there's many different phases and stages. They have a bunch of bottlenecks. Like there's a lot of data being moved around and passed around. So I think for those reasons, it's not as much of like a no-brainer. To give an example, I think there's been a lot of people in the ML world that have tried to compete with NVIDIA and make custom chips for ML. And I think very few of them have succeeded. Arguably, there's maybe even no success. And so you could also imagine maybe a similar situation playing out with ZK for at least a long time. I mean, now people are talking about AI inference chips, and there's this new crop of startups, and from talking to my friends, some of them are excited about some of the startups, but like, I think people are still very far away. But AI is also like Nvidia's market cap's about like $3 trillion or something. So, it's just in a different stage of maturity, and I think it might be a while in ZK world before we get to that, and that makes sense. On the other hand, I don't know, like maybe in 3 months there will be like trillions of proofs and trillions of cycles, and we're like, oh, like we actually really need this. I think I myself I don't have like a super strong view on it.
Yeah. Great. Well, is there anything else you want to jam on? I feel like this has been a full tour from the architecture to the use cases to how everything like fits together.
Yeah, I feel like we covered a lot of stuff.
Yeah. Thanks for the mini lesson in how Starks and Fry and everything work also.
Oh yeah, for sure. It's fun to talk about because I think you're like one of the few podcast hosts that really did your like research.
Yeah. Well, I think at some point we got to just pull up a whiteboard and work through the math, because I don't know if this as a medium is very conducive to it, but it would be nice to do that.
Yeah, for sure.
Thanks so much, Uma.
Thank you for having me.
Hey, I have a small ask here. If you've been listening to these conversations and want to support what we're doing here, I would really appreciate if you leave a rating and a review for the podcast. It might seem like a small thing, but it actually makes a big difference to help other people discover the show also. Thank you, and I'll see you again soon.